Hello, it's Keith here, and this is lesson 16 of the multi-platform series of Z80 programming tutorials. We're going to be looking at my tile sprite engine again this time. It's multi-platform, of course. You can see it here running on the Sega Master System on the right and the Amstrad CPC on the left. This time we're going to be looking at the Sprite Code. Now you see, although it was designed originally as a tile engine, because the tile map can be any size and any screen position, we can use this for drawing sprites that are made up of 8x8 blocks, effectively tiles. And you can see some here. You can see there's this Chibiko character going off the screen here, and that little Yokubiko going up and to the right. Now they're different sizes, and you can also see they can be partially on and partially off the screen. There's some clipping code going on to work out how much of the sprite needs to be cropped and redraw it accordingly. So I think this is a fairly effective sprite routine actually, and while there are some disadvantages in drawing it in 8x8 tiles in the sense that you need to maybe recalculate the memory positions a bit more than necessary, there are some advantages as well, that we can use all of the technologies of the tile sprite routine. In other words, the fast filled, solid filled tiles, the skip tiles, and the replication of tiles. You know, we can have the same bitmap 8x8 block reused multiple times in a large tile. You know, these are big advantages when it comes to a large game. With Chibi Akamas, I had to do a lot of tricks to make my large boss sprites smaller because they were simply using up all the system memory. If I'd had the ability to reproduce 8x8 blocks fast and efficiently, that would have actually probably been a net gain in terms of speed and sort of memory saving over the loss of the extra code needed to handle the tile code to do the sprites. Now on the left, the Amstrad CPC is a pure software system. On the right, the Sega Master System is a sprite based system, and the Chibiko is transparent there because it's actually using hardware sprites. There is a second copy of the tile sprite code that is designed solely for hardware sprites on the Master System, but there is also the ability that if I artificially limit the maximum number of hardware sprites on the system, if I can remember where the code is to define the limit of the hardware sprites on the system, the code will actually do a fallback, and it will switch to, rather than using hardware sprites, it will use the tile map to simulate software ones. If we just wait now, you see that one's still okay. But now when this comes fully on the screen, it's now using the software tile map to simulate a sprite. And as soon as it starts going off the screen and it no longer needs more than 32 tiles, it goes back to hardware sprites again. Now obviously using the software tile map in that way isn't very good. You could see it was quite jerky because of course there's only one tile layer on the Master System. But the point I'm making is we can actually do some tricks here and use hardware sprites where available, and use the tile map to simulate sprites where they're not. So that's another feature of the code we'll be looking at today. Okay, well we're going to go over to the source code and we're going to discuss how I made this work, because I think it worked surprisingly well, as I say, considering really all I did was reuse the existing tile map code. Now, there's a couple of things we're going to need to discuss. The main one is going to be, of course, drawing the sprites. We've got a sample program called Draw Chibiko here, which is the larger vampire sprite, and Yokubiko is the smaller alien sprite. So here it is. Now, we've got some code here. We're moving the Chibiko down and to the right by incrementing the XY position here. The XY position is in pairs of pixels. We're using some logical screen coordinates so that we can have sprites partially off the screen. So BC is our XY position. DE is a pointer to our tile map definition because the sprites are effectively a miniature tile map. We'll have a look at that in a second. And HL is the size of the sprite in tiles. So ours is 6 tiles wide and 7 tiles tall. So let's have a look at the tile map definition. Now, as before, the tile map is effectively kind of rotated 90 degrees. Effectively, we're going down the tile map kind of like this, in a zigzag format. So this is actually the first column of the tile map, not the first row. So again, as before, these are pointers to the bitmap data within our code on the software systems. On the hardware systems, it's actually a pointer to the tile number and any other data we would want to write into the tile map. Now, on the Master System, we're able to use the same bitmap data for sprites and tiles. That's how we're able to switch between hardware tiles and the hardware sprites, where there are enough hardware sprites. So you can see that is the data. And of course, the Chibiko bitmap data is actually a file that's been included in the native format of the system, split into 8x8 blocks. Everything's being done in 8x8 blocks. Now, the bulk of the work that we're going to be looking at today is done by this sprite routine. The rest of the work is actually done by the same Tilemap code, as we've already seen. There is a special version of the code, of course, for the Master System hardware sprites, but we're not going to look at that today. It's beyond the scope of what I'm looking to discuss. You can look at it yourself. It's included in the sources. I'm really just discussing the common code of how we're cropping sprites today and how that works with the tile system. Of course, this will probably be interesting to you if you were looking to write your own sprite drawing routines, because you're still probably going to need to clip the sprites when they're partially off the screen and deal with the problems that causes. Now, the coordinates I'm using within my code here are based on pixel pairs. Now, my visible screen is 256 by 192. Even on systems like the Amstrad CPC, I'm shrinking the screen. Now, we're working in pairs of pixels, so our visible screen is 128 by 96, half 256 by 192. Now, so we can crop sprites, we need coordinates where they're partially or entirely off screen so they can come in. And as you saw, Chibico was off the screen for a long time, started coming in, came in, and then started disappearing and then completely disappeared. And that's because there is an invisible area around our screen. Now, that invisible area is even, so it's 64 on both sides here, and it's 80 and 80 on the top and the bottom. So we've got our visible screen right in the middle there. So here we're defining the size. This shouldn't really change, but just in case it does. And we're clipping part of the sprites for the edges of the screen. Now, our code can't actually draw at the very edges of the screen. There's a trick. I will show you it. Because of the memory layout of the screen, it's very difficult to draw in certain positions. If our sprite was sort of half on off the screen, for example, we would need to potentially remove half a tile. The trick is very simple. You see this nice thick border around the screen. Well, if I turn that off, you will see that the reason that border is there is to hide the fact that we can't actually draw right at the edge of the screen. So we're effectively avoiding the problem of having to draw half a tile by simply covering up half a tile of the screen. Yeah, it's a cheat, it's a trick, it's a cheat if you want, but it saved a heck of a lot of code, and I think the result is reasonably acceptable. So here we go, here is the code now without the border, and you can see there's garbage being drawn at the borders, and as the sprites come on and off the screen, you will notice that there are times when half of them is not being drawn. That one's a bit too fast for us to see. Maybe that Chibico will come back soon. There it is, and you can see occasionally the top line is glitching there, and as it goes off to the right, the half tile is not being drawn because there is no code to do that, and the reason is it would be quite different code. It would be quite complex to calculate. So rather than bother with that, I've simply covered the garbagey area with a nice border, and I've created a piece of code called clear border and that is coded in each system to be as fast as possible using stack abuse and working within the limitations of the screen coordinates, and that gives us a nice looking screen without really any extra code. So as I say, it's a cheat, but 8-bit coding is usually about cheating. It's about giving the best result as fast as possible within the limitations, and I've saved a lot of memory and a lot of extra work by just putting a nice border around the screen, and it still looks quite good. So yep, it's a trick. I am fully honest about that, and that's why you will not see any code that works in half tiles in the Sprite code. Okay, so here's our draw sprite routine. We're using every single register going here. We're going to use the lot. Now the first thing we're doing here is we're going to work out if we need to crop our sprite, and so what we're going to have to do is look at the position of our sprite and compare it to the edges of the screen. We're going to use some markers here to denote if the sprite needs cropping. We're going to use this shadow register D, which is going to be 0 if the sprite doesn't need cropping. It's going to be non-zero if it needs cropping. We're going to check it all the way down here, and then we're going to run a crop routine if it needs cropping. And we'll just quickly look at that because this describes the other registers. IX and YY are defining the edges and how much needs to be taken off each side. IXL is the left side, IXH is the right side, IYL is the top side, IYH is the bottom side, and so if anything needs taking off one of these sides, this routine needs to be called, and it will make the changes required. And the changes required are going to be changing the start position of the address in the tile map we start drawing, changing the number of tiles to draw, and also changing the number of tiles to skip. Remember, we go down the tile map, but if we've taken one tile off the bottom, when we get here, we'll effectively need to skip one tile within the tile map before we start drawing up here, because we won't be drawing that tile there. And so all of that needs to be calculated, but if we're not cropping anything, then we don't need to bother. Now, effectively, our coordinates are in quarter tiles here. So we're effectively skipping 2 bits because we want the full tile coordinate here. So what we're doing here is we are taking the left coordinate, we're comparing it to the minimum x, and if we've not gone negative, then the sprite is entirely on the screen, so we don't need to crop the left hand side. If we do need to crop the left hand side, we're going to work out how much. So we need to work in entire tiles here. We're then comparing to the H register here, which is the width of the sprite, and if actually the entire sprite is completely off the screen, then we're just going to return because there's nothing left to show. However, if that's not the case, then we're going to need to work out how much we need to remove. We're setting the marker to denote we need to remove something. We're then storing the amount we need to remove, but we're retaining the bottom 2 bits, which are the quarter half shift, so that we can have the nice smooth scroll still, because even if we're skipping 1 or 2 tiles from the top, we need that relative position compared to the tile map. So that's what we're doing there. So that's doing the left side. We're then doing the same for the right side here. So we're comparing here the starting position, adding H 4 times, because remember there's 4 logical units per tile. We're working in quarter tiles, and then we're comparing to the effective visible right hand side of the screen. And again, if we have no crop needed, we're skipping down here. If there is a crop needed, we're storing the amount we need to crop in IXH, updating our marker again, and then we're doing the same for the top of the screen here, and then the bottom of the screen just here. So these are all basically the same, just with the different coordinates. So we're doing the 2 sides, the top and the bottom. Now once we get down to here, we've either decided we don't need to do any more cropping, or we've calculated the crops. So what we're doing now is we're loading in D from the shadow registers into the accumulator, and we're setting the default unused tiles at the bottom of the tile map. Now, as I say, by default, if the entire tile map is on the screen, there would be nothing to skip at the bottom. But if we've removed 2 tiles from the top or the bottom, then we're going to need to skip 2 to get to the correct position for the next line of the tile map as we're drawing, because as I say, we draw down and then across. So this is the default, but this will change if we're going to crop our sprite, and it's this code here doing the cropping. So we'll take a look at that cropping code right now. So this is the code that's doing the cropping. So basically it's taking IXL here, and if there's something needs cropping off the left hand side, we're going to effectively remove an entire strip from the tile map data. Remember, this is the logical tile map data, which is the pointer to the byte data that we're going to use to draw that strip. So we need to remove an entire strip, which is of course the height times 2 bytes per tile. So we're doing that there. We're adding that for each strip that we need to remove there from the left hand side, and then we're doing the top. Now to remove a tile from the top, we effectively need to just move 2 bytes. That will effectively move us down 1 line, because remember we're going vertically and then horizontally. So we're doing that just here, and then we're doing the bottom here. Now what we need to do to remove a tile from the bottom is, as well as just subtracting it from the height of the tiles, we need to skip the number of tiles we're removing from the tile drawing code, and that's what this is here. And so what we're doing here is we're taking the amount we've skipped from the top plus the amount we skipped from the bottom, and we're adding that together. Now of course we'd only need to skip from the top and the bottom if our sprite was so huge it didn't fit on the screen all the time, but why not? You know, maybe we want to do that. It's within the capabilities of the code, to my knowledge, to do sprites of really any size. I mean, you can even use multiple tile layers, so it could do it. So that's what we're doing there. And then we're reducing the height, the actual calculated number of tiles we're going to tell the tile map code to draw. And we're doing the width, reducing the width accordingly, depending on what we need to remove from the right hand side. Now we need to alter the number of tiles to skip for the bottom, but because we don't need to do anything like that for the right hand side, and the left is affected just by the skipping of the start position just up here. So that's all we need to do there. So once we've done that, we just return, and that will change our memory address to start drawing the tile map, and also the skip for the bottom of the tile map, and of course the width and the height have been changed as well. So that has now done everything we need to do to initialize our tile map code to draw the sprite as a miniature tile map with the cropping considered. Here we've got some code that's going to check if we've got enough hardware sprites left to draw this sprite on screen. Now this is zeroed at the start of every frame, and what we're doing here is we're calculating the width and height of the miniature tile map, the sprite, and seeing if there's enough hardware sprites unused to do that. Now this code's very crude, it doesn't take into account transparency. We can have a 32 by 32 set of tiles, but half of them could be completely empty. The code allows you to do that. This code doesn't know how to do that. It's not that smart. It it takes the X and Y, multiplies them together and sees if there's enough hardware tiles left. It's not smart enough to do any more than that. So that's a limitation there, but I think it's okay, at least for this stage. Now the hardware sprite code is of course completely different. It mimics the software sprite code, software tilemap code, but it's completely different. I'm not going to go into it here. I don't think it'd be very interesting to most people, so we'll just skip over that. Now what we've got next is some platform specific code, and this is for the software tilemap systems. It's effectively calculating the memory address of the screen memory, or on the Sega Master System, the tilemap address that we're going to write the data to. So this is different on every system, but effectively at the end here, we have now got D and E, and then later IXH, IXL, as the address that we're going to need to write the tiles to get our tilemap visible on the screen. As I say, I'm saying tilemap here because remember, a sprite, as far as this code is concerned, is a miniature tilemap. So that's what we're doing there. Now we've got some code here to run the alternate code for the Amstrad CPC. Remember, the Amstrad CPC, the tile code is very hard coded to the screen coordinates, and so to draw 4 pixels down vertically, we're actually using an alternate version of the code for speed. Horizontally is not so bad, we can just use our regular code and just move our position, but vertically moving half a tile down is very complex because the memory coordinates for 8 pixel jumps is very special. So if we start 4 pixels down, that code needs to be in a different place. And this is why, as I say, drawing that border around the screen solved our problems of having to deal with drawing half tiles on the sides of the screen and things, which again could have been quite seriously complex in some cases. So that's what we're doing there. But if not, we're just using our regular draw tiles routine. But either way, this is basically now just using the regular tilemap drawing code to draw a miniature tilemap at a memory address that we've calculated here. The hardware tilemap version is just here, but again, it's basically the same, just calculating the memory address here that we're going to want to draw to. And as I say, the code there is dealing with that. And that's really all there is to it. I mean, basically, when you want to do cropping of sprites, you just need to compare to your extremities of your screen, your logical screen coordinates and your sprite size, and work out the changes to your sprites accordingly, and also then make sure you've got code that can quickly remove the data or skip over the data that you don't need to show. And ironically, that's why this tilemap code works relatively well. With regards to Chibi Akuma's, the original game, there were 2 versions of the sprite code. There was one that was very fast for drawing a sprite that was entirely on the screen. It had no checks. It would just start at sprite start and run to sprite end, and it would go like this as fast as it could. And then there was the alternate one, which was for when the sprite was partially on the screen, and it was much more complicated because it needed to have loops to say, well, have I drawn the correct number of pixels here? Yes, we'll start again. Do I need to skip any pixels before I start drawing? Yes, well, skip them. And it was much, much more complex, much slower than the dumb one that just said, right, well, here's my data, draw, 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 don't ask questions, don't think. And as I say, this one, because it's working in 8x8 blocks, while that's a disadvantage in some cases compared to just speed copying 32 consecutive bytes, that while there's some disadvantages to it, there's some advantages to it as well, because once you're already chopping everything up into 8x8 blocks, well, skipping one strip of 8x8 blocks is a lot easier for the tilemap code than it was for my fast sprite code within Chibi Akuma's. My fast sprite code couldn't do it. So as I say, hopefully there are some advantages to this, and if I get time, I'm hoping to have a go with this and see how it works in a sort of larger game. You know, I kind of get the feeling it would work extremely well, and I could say my gut feeling is it's probably not worse than the Chibi Akuma's code, and it's arguably quite a lot better, because things like the Trojan Bunny tank in Chibi Akuma's episode 2, which was nearly the full height of the screen and had animation and things, that was really eating up the system memory. And the grand finale of that game, where there were sprites like they were actually compiled sprites, but they were full screen and things, and that it was very complex to get very large, very fast objects on the screen when you were I've not got enough spare memory to do this, I can't draw sprites this big, and how do I cope with the fact that large areas of my sprite are black, and I don't want to really store them in memory, but I don't want to chop this object up into more small sprites because that's causing other problems. So as I say, I think there are some benefits to this kind of code, and hopefully it'll be useful. Anyway, Hope you found this interesting. If you have, please like and subscribe. You can download the source code to this whole Tile Sprite series. It works on the Master System, the Spectrum, the Sam Coupe, the Amstrad CPC, and also the Game Gear. It could be ported to other systems fairly effectively. I don't think it'd be particularly difficult. It took me about half a day. For the software-based systems, the hardware ones, it depends on the system. But as I say, hopefully it's at least a good starting point. As I said before, if you find this too complicated, take a look at my simple series where we just looked at simple 8x8 sprites and sprites that are entirely on the screen. That's much easier. And if you can make a game that doesn't need partially on the screen sprites, partially off the screen sprites, you're going to have a much better day. So that's what I'd suggest you look at. Anyway, I hope you have a lot of fun and I wish you the best with your Z80 programming. Thanks for watching today and goodbye.